In Chapter 10, we're going to go ahead and take a look at probability. There's different types of probability models dealing with discrete and continuous situations, but there's still some basic rules that apply to each one. Now, probability is really the science of chance behavior. And you might think, well, it's chance, it's random behavior, but often in the long run, there ends up being a predictable pattern that occurs. And so then we can go ahead and use the idea of probability to draw conclusions when we're dealing with random samples or random comparative experiments. Now, a random phenomenon, there's no way to predict what's going to happen next. But a lot of times with random phenomenon, there's an overall pattern that ends up showing up once that has been done multiple times or a large number of times. And so if you end up just randomly choosing an individual and measuring their height, and you keep doing that for a long period of time, you end up getting what's referred to as a normal distribution. There's a certain pattern that showed up over time. Even though when you randomly just choose an individual, you don't know what their height's going to be before you choose them. Same idea with a coin. Now, let's talk about independent. Independent means if you go ahead and do something now, it has no effect on the next time that you do it. So if you flip a coin, record the results, flip the coin again, the second time is independent of the first time because what you did the first time it should have no effect on the second time. Now, flipping a coin is independent. You would expect the probability of getting ahead to be 50%. Over here on the side, we have the number of times you're flipping a coin going across the bottom and the proportion of getting heads going up and down here. Here we flipped the coin once, and you'll notice on the black time we got ahead the first time. You got several heads here in a row, but then you started getting some tails and it started pulling it down. Now if you continue to do this many times, even like up to 5,000 times, it ends up starting to level out at a 50% chance of getting ahead. Well, the red is another example that was done. So let's go ahead and try this with our probability applet. Now I'm going to go ahead and change it so that we're doing 40 tosses here. So I'm going to toss it, and it's going to go ahead. You'll notice we had a couple of tails here, and we're looking at portions of getting heads. But you notice once we got going, it started hanging out in the middle here. And we could go ahead and repeat this several times. But as we do this, as you go across here, it's going to consistently hang out and level out at a height of about 0.5 or 50% for the more tosses that you do. You notice there is some variability up and down, but the more tosses we do, it will eventually get really close to 50%. If you only do a few small tosses, back here you notice it varied a lot up and down. But the more tosses you do, the more it levels out. So hence you want to do a larger sample size whenever you can, or more trials. Now two events are independent once again when what you do the first time has no effect on the next time that it happens. Now not everything is independent. So sometimes what you do one time affects what you're going to get the next time. Here's an example. Suppose you have a bunch of coins laying on a table. Half of them were tails and the other half were heads. You reach down and you go ahead and you pick up a coin. Now, if you keep that coin in your hand, it's no longer 50% for going back and getting a second coin for being a head, because there's no longer an equal number of heads and tails left there, because there were to begin with, but you chose one and you kept that in your hand. And so then there's more heads or more tails than the other one. Now, if you were sampling with replacement by taking that coin, picking it up, looking at it, recording the results, and then putting that coin back in there so there's still equal number of heads and coin, or heads and tails, then it would be independent. But if you pick that coin up and keep it and then go back for the second one, it's no longer independent. Now let's start talking about the probability models. We need to first of all talk about your sample space. Your sample space is basically the set of all possible outcomes. Sometimes you can list all the possible outcomes, or you'll go ahead and just say that it's between this and this if there's a lot of possible outcomes. So if you're looking at all the numbers between a 1 and 2, you would not be able to list all the numbers between 1 and 2 because there's infinitely many decimals numbers between a 1 and a 2. But every probability situation, so if we're looking at the sample space of flipping a coin, we only have 2 possible outcomes, a head or a tail, so that's our sample space. And then we know the probability for each one. The probability of getting your head is 50%. Probability of getting a tail is 50%. Now, sample spaces can vary depending upon how the question is phrased. So here we have a basketball player shooting 3 free throws. What are all the possible sequences of hits and misses? Well, you could have a head followed by a head followed by a head, which we have listed here. Or you could have 2 heads followed by a miss, which we have listed here. Or you could have a head followed by a miss, and then you could have a head, which is listed here. Or you could have a head followed by 2 misses, and then we have that listed here. If you did the lower branch where you started out with a miss instead of a head, you would then have all these possibilities listed, all 8 possibilities. Your sample space would be all 8 of these different sequences that could occur. Now, if you phrase the question a little bit different, still shooting 3 free throws, what's the number of baskets they could make? Well, it's possible they could make none of them. It's possible they could make 1 basket, or it's possible they could make 2 baskets, or it's possible they could make all the baskets. So in this situation, the way the question is phrased, our sample space would be 1, 2, 3, and 0. Now down here, your sample space, if you're looking for weight gain, would be all numbers greater than or equal to 0. You can't really list all the possible weight gains because you can have part of a gram being gained, and so it's just all possible positive numbers greater than or equal to 0. Now, just to review, suppose you had the probability of something, but you knew it would never happen. So what is that probability? Well, the probability of something never happening is 0, or 0%. But if you know it's always going to happen, the probability of something always happening is 1, or 100%. Now consider this data here where you're given the age of the first birth of their child. For women, under the age of 20 is 25%, between 20 and 24 is 33%. If you're over 25 years of age, would you be able to figure out that percent? I would assume most of you would, because all 3 of these percents, most of you would know would have to add up to 100%. And so you'd figure out these here, add these together to subtract from 100, and you get 42% for this one. Or suppose I said the question, what's the probability that a woman has her first child of age 24 and younger during her years? Well, you'd probably just go ahead and add these 2 percentages together, and you would be right with that. And now that leads us into our probability models. All probabilities range from 0 up to 1. 0 meaning it would never happen, 1 meaning it would always happen. Now, the probability for your whole sample space has to add up to 1, meaning all your probabilities add up to 1. Well, going back to your tails and your heads for your coin, it would be 50 plus 50, 50% plus 50% equals 100%, or 0.5 plus 0.5 equals 1. So it does add up to that. And that's what we were dealing with here. When we said, well, we want to go ahead and figure out what this is, we added them together and subtracted it from 100. Because we know they all have to add up to 1. And this one here is saying if we want to know what an event is, we could actually just subtract what we don't want to come up with that. Oops, and I went the wrong way. And that's kind of what we were doing here. We wanted to know the probability of this. So all we did was subtract these two from our 100% to be able to get that. We subtracted what we didn't want to get to what we wanted. Now, if two events are disjoint, meaning they have no common outcomes, to figure out the probability of one or the other occurring, all you have to do is take the probability of the first one plus the probability of the second one. And this works when they are disjoint, where there's nothing in common. And that's what we were doing here. To figure out the probability of 24 years of age or younger for your first child, we added these two groups together. These are disjoint. You're either under 20 or you're between 20 and 24. So we added these together to two disjoint sets to be able to get what we were looking for. If you go ahead and flip two coins, you could either get two heads, or a head followed by a tail, or a tail followed by a head, or you could get two tails. This is your sample space. Each one of these four possibilities has an equally likely chance of occurring, so the probability of each one of these occurring would be 1/4%, or not 1/4%, 1/4, or 25%, or 0.25. If you wanted the probability that you only get heads or only get tails, that's only two heads or only two tails, and they're considered disjoint because there's nothing in common between these two, you would take the probability of two heads, which is 0.25, plus the probability of two tails, which is 0.25, and add those together and get 0.5, or 50%. We also have to deal with a discrete sample space. In a discrete sample space, only certain numbers or possible outcomes show up. An example of that is if you're dealing with a typical six-sided dice. If you roll a dice, you're only going to get a possible outcome of a 1, a 2, a 3, a 4, a 5, or a 6. Each one of these 6 possibilities has an equally likely chance of occurring. So the probability of each one of those occurring is 1 out of 6.